everyone. My name is Elias Fallon. I'm with Keekso, but I'm also one of the members of the Tiny Machine Learning Auto Machine Learning Working Group. Welcome to the final of our tinyML Auto Machine Learning tutorials, a deep dive with Imagimob. As you might know, we've been doing these since our forum back at the beginning of June, kind of giving everybody a deeper look into each of the tools we highlighted. So we have to thank our Tiny Machine Learning strategic partners for all helping work together to bring this industry to the next level together and sponsoring all these activities. There are always lots of things going on with Tiny Machine Learning. So the tinyML Asia is a virtual event coming up at the end of November. Take a look at the URL there to sign up and find out more about the event. You can always join the meetup communities or the LinkedIn communities using the QR codes here or the URLs to get more information. There's always lots of new events getting posted there. You want to keep up with them. As we're going through the talk today with Imagimob, we are recording the video, and we've recorded all of the deep dives that we've done over the last couple of months. And they're available at youtube.com/tinyml. You can also see all of the other talks that happen as part of the tinyML speaker series. So take a look there. That's all of my intro. I want to introduce Alex and Sam, some of the engineers from Imagimob, who are going to take you through the deep dive and teach you a lot more about their tool set. So Alex, Sam, take it away.
Thank you, Elias. Yeah, so there we go. Welcome to the deep dive with Imagimob. We're going to show you how you can go to production with your tiny machine learning applications using our platform, Imagimob AI. And my name is Alexander Samuelsson. I'm the CTO and one of the founders at Imagimob, and I'm leading the development of Imagimob AI, our platform for tiny machine learning development, which is one of the most powerful platforms for tinyML development. And I've got more than 6 years of experience designing tiny machine learning applications from project start to actual commercial launch. So we have some applications that are actually available on the market, which gives me kind of a unique level of experience in this market. And with me today, I have Sam.
Hi, everyone. So my name is Sam Alatian. I'm head of customer success at Imagimob. I'm leading the application development side at Imagimob. So that means helping customers put models into production. So like Alex, I have more than 5 years of experience with the machine learning at the edge, and that goes all the way from commercial conceptualization to commercial launch and long-term maintenance of models to make sure that they're actually doing what they're doing out in the field.
So what we will be going through in this deep dive is, first we'll tell you a little bit of some background to Imagimob, what we've been doing through these years, and then we will tell you about the platform, what it is and what you can do with it. And then we're gonna show you how you can build tiny machine learning applications with the state of mind of going into production already when you start building your applications. And we're gonna do this with 2 concrete examples. So we'll show this from the perspective of building an audio classification application, which is kind of like a smart home application, which allows you to increase the light intensity or decrease the light intensity of your lights through voice commands. And we will also talk about this from the perspective of a fall detection application running in a device in a belt buckle, detecting falls, targeting the elderly. So first of all, a little bit of background to Imagimob. We've been running machine learning projects for embedded devices in 2015. And we've done this in the form of many different projects with small and large companies from all over the world. So we've run more than 40 tinyML machine learning projects. And as you can see here, here's smorgasbord of different applications that we've built in the past. And one example here, you see a watch here. This is a fall detection application targeting the elderly. This is something that you can buy. It's on the market. And this watch has a motion sensor and an MCU. And if the wearer falls over, it will send an alarm and notify this person's relatives. But we've built many different applications. We've done predictive maintenance in pumps. We've done gesture control in earbuds. And going through building all these applications led us to build Imagimob AI as a platform to allow us to go through these projects, faster and with higher accuracy of the models.
So shorten the time to market.
Yeah. So we then released Imagimob AI to the public, and it's an end-to-end development platform for tinyML, which allows you to do everything from collecting and extracting the data from your devices or machines, through annotating that data and analyzing it, through building and training great models, all the way to optimizing them and packaging them and putting them on the device. So this is what we will use throughout the presentation. So with that, let's get started. So
yeah, so we've kind of broken up this presentation into a number of different parts that will take you through the steps of building production-ready models and the development cycle of machine learning, especially for tinyML. So the first step, and arguably one of the most important steps, is the conceptualization. So in this part, it's about kind of really thinking about what do you actually want to achieve with your model? Where is it going to be placed? What kind of data is it going to be subjected to? And even what kind of model you want to build, whether classification, anomaly detection, or regression model, what makes the most sense in this scenario. So for example, in this presentation, we'll look at keyword spotting and fault detection. But if you were to build a keyword spotter in a home as a smart lamp versus one in a factory, that can differ drastically. So if you're in a home, you would be subjected to different kind of environmental noises and sound characteristics, even with the reverberation. Whereas one put in a factory is going to have like a lot of more like working noises, more like machines going off, but it's also a large hall without so much echo. And then likewise for fault detection, if you mount the IMU inside of the collar and intend it for construction workers versus putting it in a belt and intending it for elderly, that could drastically change how you collect the data. And coming up with a good concept kind of ties into the next part, which is building a good data collection plan that covers the kind of data you want to collect.
Yeah, so if you think deeply about where will the model be situated, how will my product look, how should it behave, and what kind of surroundings will it be subject to, well, then you basically have a guide, a foundation for your data collection and your data collection plan. Because when you make a plan to collect your data, you should think about the lifetime of your model. So if you already know, if you figured out how the device will look, how it will be mounted, and who your target group is, then you can make a very good plan for, for example, if I do fall detection for the elderly, they are less active than a construction worker having a fall detection device. And it's mounted in the belt buckle instead of the collar. If you don't do this, and we see this all the time, well, you can spend a lot of time collecting data that goes to waste, that you will not be able to use, or you will have to collect data over and over again to get all of those edge cases that you could have figured out from the start. So, okay, once you have a good data collection plan and you know what kind of data to collect, then the question is, how do you get that data out of your devices, and how do you understand what data you get? So what you see here on the slide, there is a sensor signal from a motion sensor, from an IMU in a belt buckle. And as you see on that sensor data, it's very difficult to understand what's actually going on there. So if you jump to the next one, Sam. So that led us to develop Imagimob Capture Server, which is a part of our platform, which allows you to quickly integrate with any kind of sensor or machine. So you'll do a tiny, you have an interface, you make a simple integration in your device, whatever you want to collect data from. And then you can receive that data over Bluetooth or Wi-Fi or through a wired connection. And you can capture that on your laptop or a Raspberry Pi or any kind of computer. And it also allows you to collect metadata together with the data. So here you see the same data, but also with a camera feed from the computer, giving you the information of, okay, what was actually going on? Someone was falling, and what was the direction of the fall, and how intense was the fall, and so forth. So this is really crucial, having a data collection platform with the ability to sometimes have metadata, and also to get everything, synchronized and structured, not having any package loss and so forth. So now we're at the state where we have, imagine that we have collected a lot of data. So now it's time to jump into the platform. Right, Sam?
Yeah. So here we have the exact same data that we saw before. So we have the signals, but now we're looking at it in the platform. So you can actually visualize the signal data, and this could be any kind of time series signal, but here we're looking at the 3-axis IMU. And we see exactly what happens in the sensor data. So for example, when the person was turning, when the person was falling, and also when they are getting up, where we can see each of those parts. And so this is a very important concept, and that this is something we've been doing for a long time, which is that you can't build really good models if you don't understand what's happening with the data. And this goes both for actually the positive data, so how you experience different falls. For example, now we're looking at the sensor being mounted to the belt, so you have kind of a free fall effect. But we also looked at the sensor connected to a wrist. So you would expect that when you fall, you would have the free fall effect. But we didn't see that, because the reason is that the person, when they fall, they protect themselves. So they throw their hands forward, and you don't get the free fall effect that you would expect. So this, you make a hypothesis, but you actually see the results from the data.
And also the data is the entire foundation to the model. So knowing that your data is sound and that it's properly annotated is your entire foundation for the model.
Yeah. So now we're looking at IMU, and if we were to kind of jump into a different data set, this is an audio data set. So if you were to play through it, and I am not sure if you guys can hear, but there is an audio being played that corresponds to down and up. And here we show a part that Alex will later go into, but we showed the time series data, but we also showed the spectrogram data, so that you can actually visualize different kinds of preprocessing and see, okay, if I were to use time series data, this is what it would look like. But if I were to use Fourier transform data, that this is what it would look like. And then kind of once you're at this stage, then it's kind of the annotation part. And the annotation is very simple. So if I highlighted the section, I would create a new label by saying that this is let's call that down.
Hmm.
It's as simple as that. And then if I wanted to get rid of the label, then I just hit delete and it's gone. We tried to make it very easy to analyze and label the data, but we also have some features that we're looking into to make it even easier. So one thing we're looking into for the future is to use machine learning to automatically label your data. So when you have 1,000 files, you don't want to go through each one and label each instance. You can build a model that can do this for you, and it will actually perform even better. So you don't have the human error of building these.
So you only have to label a part of the data set, and then you let the model label the rest.
Exactly. So so this part is very important. And then once you've kind of got a feeling for the kind of data you're working with, then you can move on to the actual model building part. And the first step of that is the data management view. That's what we call it. And in this view, you can see all of your data sets, and you get some information about the labeling and things like that. And two things that can become immediately clear in this kind of view is that, for example, we have very little background data compared to up and down. So we see up and down, and then we see there are only 8 background files. So we already, if this was a production model, we know that this is not enough background data for the model to perform well.
Yeah, basically, it only has the 2 classes that it needs to recognize, up and down, and it needs a lot of other words and a lot of different background environments to be able to separate that well.
Yeah, the combinations of, let's call it negative data, is a lot more than positive in reality. And the other thing is we give information about the properties and of the data. And for example, one customer that we had from the automotive side, they included data for their project, but half of their data was at 3 hertz and half of the data was at 30 hertz. So that obviously led to a very poor model. And this feature, you can quickly go through your data set and sort by frequency to make sure that all of your data is the same frequency, or all of your data is the same dimensionality. So you don't have some of the data as stereo and some of the data as mono. And here you can also balance your sets and things like that. So you have a lot of functionality to work with.
And circling back to production, this is more common than you might think. If you have a really large data set, that you have just a few files, few recordings where you happen to record at the wrong frequency or forget to annotate some data, actually have a big impact on your model. We have this golden rule that if you have 10 good data samples and then you have 1 bad one, improperly labeled or whatever, that one sample will destroy 10 good ones. So only getting, a little bit of your massive data set wrong can be the difference of having a good model and a very good model.
Yeah. So it's always worthwhile to kind of go through this and make sure everything is fine with your project. Especially when we're talking about production, you're talking about thousands of files. So it's easy for human error to show up in this. And then moving on, we talked before about preprocessing. So can you tell us more about that, Alex?
Yeah. So preprocessing is an extremely important part of your path to production. So once you have good data, it's properly annotated, most of the time you want to actually process that data before you put it into the model, because that allows you to reduce the raw data into something more compact while still keeping all of the important features, which in turn will allow you to have a smaller model with the same level of performance, And so it will run better on an embedded device, but it also has the benefit of actually requiring less data. So the model won't then have to learn how to do all of this processing and get rid of noise. You can help the model and save a lot of time and get better accuracy. So we have a library of pre-processing functions to get you started, which you can piece together into a pipeline like you see here. So you have this library of functions that you can use, but we also have the functionality for you to add your own custom pre-processing. And that's also quite common. If you're going to production, you have a new kind of sensor that we haven't made pre-processing for, then you can input that here. Or if you want to use a function that we have created but make some tweak to it, you can do that. And we also have preprocessor packaging, already pre-made packages, like what you see here is an audio pipeline for generating these nice spectrograms that we saw earlier. And the good thing here is that all of these preprocessing functions, they will work on the edge. So at the end, when we go to the edge device, all of this preprocessing will be there, so the model will just work out of the box. But I wanted to highlight an example here to illustrate how important your preprocessing is. So what you want to look for here, so here again, we're at the audio example. We're trying to detect the words up and down. And what I want to look for with my preprocessing is that if I'm able to clearly see the similarities between different utterances of down and different utterances of up, then the model will be able to do that too. So once you've got your preprocessing set up and you're visualizing it in the tool, and you can see clear patterns, then you can move on to the next step and build models. But actually, quite small tweaks can make a big difference. So what we're looking at here, so for example, if we look at the visualization here, I can clearly see patterns here in these two down samples. So I see some highlights here going like an arc here. I see the exact same pattern over here. And then I see a very distinctly different pattern in the up sample, but then the second up sample looked very similar to the first one. So here I have a good preprocessing pipeline set up. And then if I look at this one instead, it's the same pipeline, but with some different settings, some different cutoff frequencies, some different bin sizes in the spectrograms. All of a sudden, I get a picture that is much more unclear, but also here, for example, I have an up utterance, and I have another up utterance with very different features. So you should spend some time on your preprocessing, and you kind of know when you're done, because when you can see these patterns clearly, then you can move on to the next step.
Yeah, and with the preprocessing, there are a lot of options to kind of go for, whether it's frequency transforms or filters and things like that. There's a lot of resources within the platform and online.
Yeah. And another example is we did preprocessing for human motion, and we just added some very simple functions to smooth the signal, lower the frequency, and that made it so that we could use a much smaller model and still get higher accuracy and requiring less data on the device for the customer.
Yeah. So yeah, well, we think that this is a very important part of if you want a good production model, some time needs to be spent with the preprocessing. So once you are happy with the pre-processing, then it's time to go to the model generation part and looking at different architectures. So within our platform, you have the possibility of using the model wizard. So this model wizard takes care of the model building part essentially. So it will generate different structures for you to evaluate what's best for the model, and it finds the best one. So you have the ability to kind of set some criteria for what kind of models to search for, and that might be because of some hardware restrictions or things like that. But for example, if you don't want to use any recurrent layers, you can simply set that to 0, or you can go ahead with the default. And then you set the number of structures, the number of hyperparameters, and what this will essentially do is that it will create a list of architectures to search the best model on. And so this is if for people that don't have machine learning knowledge, that they want to focus on the data and then just build good models, you can take this approach. Or if you have more machine learning knowledge, you can actually go in and look at what models are being generated. You can even edit them and create your own architectures within the platform from scratch. And you can also import architectures that you've built outside of the platform. So you can build the architectures in TensorFlow and then import them. And you can combine the two. You can import some models and you can generate some models and do the evaluation based on everything and find the best one.
And just a teaser for where we're going in the future. We're looking at ways, so as you said, Sam, now a list of models being generated and we send all away for training. But in the future, we're looking at using tree-based search, where you're able to search through a much larger space of models in a much shorter amount of time. So basically traversing through the graph where you find the best accuracy, leading to even better auto machine learning capabilities in less time.
Exactly. So once you're at this stage, it's I'll just stop to kind of say that we'll answer the questions at the end, because I can see that there are 6 questions already. So at the end, we will be able to answer all of your questions. So just be patient. So at this stage, you can log into your cloud and then send this models for training. But so since we're a bit restricted on time, I will just show some models that we already have trained. So this is kind of the cloud view, and within this, I could see everybody within the team. So the idea is that within your team, you can collaborate more easily. I could see that, for example, Dennis has been working on some keyword spotting application, and if he's doing some testing with some different pre-processing, I can check how far he's going and maybe take his learnings and apply it to my project. So it's much easier to collaborate. But I'll open the models that I have been training. So this is kind of once you finish training the models, you can see all of the different architectures and what kind of scores they've been getting in terms of accuracy and F1 score. So now I sorted by F1 score, and I can see that Imagimob AI has already selected this one as the best one with F1 score. So I could have immediately just selected that one. Within this view, you get all of the numbers that you need to make an initial evaluation for the model. So here you get the numbers of F1 score for different sets. You also get the confusion matrix for the different sets, and then some plots. Just to kind of to avoid going into too much detail, I'll show an example of how this can be very valuable. So here I can see that this model has 97%, and this model here also has 97%, and this is because most of the data is actually the non-class. So this was a bit deceiving. If I actually go to the test set and look at the normalized view, I can immediately see that, okay, this model actually only classifies 50% of my up data, whereas if I look at this one, it correctly classifies 80%. So it's always good to kind of look into the detail and not look at the overall number and make a decision based on that. But Alex will go into more details about how you can do further evaluation within the platform. And to go to the next step, you simply pick the initial model. This one seems promising. I'll hit download. So then I will get the model.h5 file. So that's the Keras model, the actual predictions, which is the actual output from the model, and some input and output data. And I've already downloaded this, so I'll just show it at the platform.
So I'm just gonna stress again that, yeah, look at some different metrics here to really try to get a good picture of which model to start investigating, because a common mistake is that you've actually have a really unbalanced model where you think that the model is really good because it gets most of the data right. And then if you look at the detail or some of the metrics, you might find out that, oh, I have very little data for one of the classes and the model totally gets it wrong, but it's not visible at first sight.
Yeah, so it's about kind of looking at the information as you go along, so you don't go all the way to the end and then realize, okay, my model's not good. So you iterate in smaller cycles and continue further down the pipeline. So now,
yeah. So
go ahead, Alex.
Yeah. So what we have here is what we call the model evaluation. It's like a detailed model evaluation. So what we got back from the training job was the predictions from the model across the entire data set. So that's what I see here. I see a recording, and down here I have the sound data still. Here I have the original label saying that this is an up sample. But up here in this graph, I have the constant predictions from the model. So what this allows me to do is essentially, perform a field test in front of my computer. So instead of taking that model that we download and putting it on the device and then testing it live, I can reuse all of my data for verification. And this uncovers things that I can't uncover by just looking at high-level statistics. Exactly. So here, I'm able to play this data back, and I'll post it here. So this uncovers, okay, when does the model detect the sounds? What's the delay? In some application, that's extremely important. For example, we were working on another fall detection algorithm for cyclists, where the fall had to be detected before impact. So then you might have really good accuracy of the model, but it detects the fall too late and the model is worthless. So here you can uncover all of those things, play through the data and see what samples the model gets right and which ones it gets wrong. And this helps a lot with finding out your next steps, because very often as you're doing this, you'll find out that, okay, here is a sample that the model could not detect, and quite often it's because the sample is bad. It's wrongly labeled, or it's just a very poor quality. It might be someone very far away from the mic, or too close to the mic so that everything peaks. And then you can clean out that from your data set and get a much better model. Other times it shows you your outliers. So you'll see, okay, my model fails to detect this sample. That's because this sample was with a different accent that I haven't had in my training data set, or it's someone saying the word in a very different way compared to my data. And that will guide you then to go out and get more data or go online to find more data to get those outliers into your model and to improve it.
So it really allows you to prepare for the kind of scenarios that the model might struggle with, to identify its weaknesses and to kind of accommodate for it. And that really drives up the performance. And even in this you can bring in like realistic data sets. So like just put in this case we have a microphone. You might want to put collect some data from like a cafe or something, or like some people talking, and to kind of test the model on it.
Yeah, so this led me to realize that we had an example here that we want to show, right?
I can show it.
Yeah.
So this is exactly what we see here, that so this is some background data, and we said at the beginning that there wasn't so much data for the background noise. And we can see here how the model prediction looks like. And then...
Yeah, so here we see that the model starts to classifying, as here the model predicts down and up. But if we listen to the sound, not sure you will be able to hear this in the video.
It's a person talking.
So what we see here is that the model is very good at classifying up and down, but it's easily confused by other speech, and that makes total sense. And so we should use this information, and it should lead us to recognize that, okay, we need to collect a lot more speech which is not up and down, just any normal conversation, and close to the mic and in the distance, to make the model more robust, to not misclassify other kind of speech.
Yeah, so in this case, the model is getting a very high confidence on just random words that this person is saying. And the reason is that it hasn't heard those words before, and now it's just kind of saying, okay, these words sound like words, whereas everything else is also words. So what's the closest bucket that I can put it into? And it's putting it into either up or down. So there are the words that it knows. So yeah, I guess the big takeaway here is that this can really help you to make sure that the model is high quality before you even go out into the field.
Yeah,
which can save you a lot of time. But then once you are actually happy with this model, then it's just a matter of opening the Keras file that we've downloaded. And there you get some information about like what kind of preprocessing was used, the architecture, and the evaluation. And we should kind of say that this model, it doesn't need to be trained in our platform. You can actually open a standard Keras model that's trained in TensorFlow, and then also open it up and convert it to edge code. But this is exactly what we're going to do here. So let's rename this file. So we're going to call it deep dive. And we'll just simply hit build edge, and we've just converted our model to edge code. And we get some information about the memory usage, so the RAM and flash, and we already know at this stage if the model is too big or if there are any issues there.
So what happened now when you click the build edge model?
So now we've taken a Keras model and then converted it to raw C code that we will see in a second. And the other thing that we've done is that we've selected this generate data compare test, and this will make sure that the model that we get is a bit match with the model that we trained in Keras within a very low margin of error. So we can see here that it's within 5 times 10 to the minus 5. So it's practically the same with some rounding errors.
So this is what you really want to see. You want to make sure that the models that I've been training and evaluating, what I get on my edge device, it's the same essentially.
Yeah. And so let's take a look at this, the models that we just converted. So what we created is essentially a raw C file. This is kind of, it's not compiled, it's the source file. So you can drag this file into your project and compile it with your normal firmware. And it has no dependencies whatsoever. So you can run this on any platform. You can run it on a Renaissance board, a Texas Instruments board, or you can run it on an Espressif board, or you can run it on the PC as we just did.
Yeah, or Raspberry Pi, whatever.
Yeah. So you can see here that everything is exposed. You see all of the functions, all of the implementations, and this means like you can actually see, and if you want to make some changes that are custom for your hardware, you can do that.
Yeah, so, and we do support generating code for tinyML accelerators as some Synaptics boards and some Syntient boards. So you can use the platform to do that. But we also really believe in having this ability to generate C code that you can run everywhere and not having it as a black box. So really exposing the code. So as you're going into production, you might want to actually trace through your code, debug it, or make modifications. And you have an example of that, the customer of us.
Exactly. So we had a customer and they had a very constrained chip, so they didn't want to run any kind of operating system or scheduler. So what they did is that they actually calculated how long it takes to go through this DQ function, which is going through all of the layers in the network that we saw earlier. And then they kind of split it up into sections. And that means that they could run a section, move to the main program, do something else, and then come back and complete it. And they broke it up into 3 steps. And you can do that because you have the source code and you can make any kind of modifications that you want. So you can even debug certain layers. So if you added a custom layer, you can debug it within the code. And it's very simple. It's 3 functions. So
yeah, so back to the slides. We have this belief that when you deploy for production, you want something transparent. Ideally, you don't want a black box. And you might want to be able to go in and debug it. But as Sam said, it's very easy to get started. It's a very simple API. And we also have pre-existing firmware examples to get you started with different platforms, as you see here on the screen. Yeah, so now we're getting close to the end of the deep dive. But what we want you to take away from this session is that when you're building tiny machine learning applications, for production, it's really important to conceptualize your product, really understand the life of the model that you want to build. Where is it located? Where is it mounted? What sensor are you using? In order to get your data collection and your data as representative of what the product will be subjected to in real life as possible. So if you really spend time with the conceptualization, and please reach out if you want help with that, that will guide you to make a really good data collection plan and get really good data for your model. And that's really the foundation. Then you should take that and analyze that in the platform to understand your data and to annotate it correctly. Hopefully, with some metadata so that you can understand that you've labeled it correctly. And then you should use your platform, regardless of what platform you're using. You should really evaluate your models thoroughly, understand them, understand how they behave, understand what data it gets wrong, which will then lead you to your next steps. Is this bad data that should be removed, or is it pointing me into a direction that I need more of this kind of data in order to make my model more robust? And then you iterate from there. You get new data, you might generate new models, and you train on the updated data and get better and better models. And then you should really, this is outside of the scope of this presentation, but you should think about how can I keep doing that even after I put the model in production, or with test groups before I go into production. And an example for that is in this project with the watch for the elderly. We built in the mechanism so that when the user or when the watch triggered an alarm, the user could cancel the alarm if it was wrong, and then we could take that data back and generate more training data from the real application to make it improve over time. So now I think it's time for us to answer some of the questions.
Yes, thank you very much, Alex and Sam. That was really great presentation and demo. Yeah, we have here the first question we have is Derek Stewart. For fall detection data capture, do you have to clip the data before the person hits the ground? Falling on cushions, as you demonstrated, would give a much different signal to a person falling on a hard surface, as would generally occur in the real world.
Yeah, so this is a very good question. So in the video here, you saw falling on cushions. We've done falling on harder surfaces than that. But yeah, it is tricky with fall detection because you don't want to hurt your subjects. But what we tend to use is a bit of a harder mattress than what you see here. And we have tried even on thinner yoga mats, but then you need some protective equipment on the person. So, and this is actually strengthening the case that sometimes you can only go so far before actually going into production or into a test group. So we built initial models with collected data in a controlled environment, and then we were able to get feedback from the real devices out in the field and starting getting negative examples which look like falls, but also real falls on hard surfaces.
Okay, thank you. Then the next question we have, it says spectrum is good to capture quickly changing processes like vibrations, but what can be approached to detect slow changes like decrease of atmospheric pressure because of weather changes, for example? This is changing slowly and not captured by a spectrogram, but what can be used instead? What if slowly changing value is covered by noise?
Should I take it or you want to?
Yeah, I can take it. So with slow changing the dynamics, what I would probably do is sample over a large period of time, and then you can kind of condense the information. So usually with the slow dynamics, you also don't need to react as fast. So if you're looking, for example, in some cases, we're looking at machine degradation over its lifetime, which could be like 10 years. So then you don't need to sample so often, but you also, you can look at a large chunk of data and then apply to take out its characteristics, essentially. So with some projects, we applied some basic statistics and took like the min max, the variance of the signal, the gradient, and the integrals, things like that.
Okay, great, thank you. Next question we have is, can ML model handle noise by itself? So train the model to ignore noise somehow. Is it possible?
It is possible. So, but the point we were trying to make here is that you can save a lot of time by applying pre-processing to, to avoid having to teach the model. that, but you can. So a common thing that you do in audio processing, for example, is that you collect your data and then you enhance your data by applying noise over it or different backgrounds, environments, and then your model will start understanding that, okay, me saying the word up means the same thing regardless if I have some noise in the background or not. So you can teach your model that, and there's ways of synthesizing data so you don't have to collect all of it. But that's the risk, essentially. If you try to train your model without any pre-processing, then you have to show the model all of those variations in order for it to be able to filter away the noise.
Yeah, makes sense. Thanks. The next question we have is from Alexander Zubin. It says, do you have support for recurrent NN?
Yes, we do. So we have support for long short-term memory layers, gated recurring units. So we have support for those kind of layers and those kind of models. But we are enhancing the platform in this area. So currently, we still only allow you you have to input the entire window of data that the model will classify. But this is something that we're improving, and we're going to allow for stateful models, which allows you to not have a window. You just output your sensor data, and the model learns these mappings over time so that it can detect short-term events and long-term events with the same kind of model without you having to figure out window sizes and things like that.
I guess we should also add, we didn't touch on this, but we also support quantization for those layers. So not only do we have them, we also have quantization for them as well.
Okay, thank you. Next question we have from Kevin Patterson. He's asking, can you elaborate on segmentation? For example, how to decide when up starts and ends?
Yeah, that's an extremely good question, which we didn't have time to really dive deeply into. How you annotate your data is extremely important. And we've seen, in different projects that reducing your labels, putting them tighter around the event, or increasing them slightly can have a massive impact on the performance of your model. So it could be the difference with, from a decent model to a very good one. And this is, so illustrating that here is like, so for example, if we take the down and up example, it's very important to annotate, put the annotations tightly around the data, but also expose the model to sounds that has, up in them. Do we have
like
puppy?
Cup.
Yeah, cup. So that the model understands when it starts and ends.
Okay, cool. Yeah, thank you. The next question we have is, Imagimob Studio is on-premise installation or cloud is possible too?
So at the moment it's Windows clients only. But in the future we will go into other platforms as well. Okay,
thank you. And then the last question we have from Mastak Fatahi, he's asking, is it possible to adapt the code for Arduino also? That we have been asked that question in every deep dive tutorial.
Nice. We're actually we've actually recently deployed a model on an Arduino board, right?
Yeah, and you don't actually need to do any kind of adapting. That's kind of what we've been that's kind of one of our important takeaways, is that this is already in C code and it's already platform agnostic. So just drag this file into your Arduino, and it should work. When you compile your model, you will just compile this as another source file. If you want to do it in C++, then you just need to add a C++ wrapper around this C code. And just to kind of give an example, before we had a project, it's not really an Arduino, but we started with an SD microcontroller, but there were some limitations, so we took the exact same model and then just put it on an ESP board, and then it worked exactly the same.
Okay, great. Thank you, Sam and Alex. So that's now last of our questions. There are no further questions.
I just wanted to say then, well, first of all, thank you for listening. And also you can head over to imagimob.com if you want to try the platform out. So we have a community edition with full functionality that you can start using today and try it out.
Yeah, perfect. Yeah, thank you again, both Alex and Sam, for that great deep dive tutorial. So again, as mentioned previously by Elias, we just want to thank all our tinyML strategic partners for committing to take tinyML to the next level together. So right now, first we have the executive strategic partners, ARM, Edge Impulse, Qualcomm, Sentient, and our platinum strategic partners are DeepLight, ClickAttack, Reality AI, Renaissance, Sony Semiconductor Solutions Corporations. Our gold strategic partners are Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SensiML, ST Microelectronics, Synaptics, SynSense, and then also our silver strategic partners, AACP, Aeon Devices, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., IBM, Imagimob, what we saw today, the tutorial, Itamis, Noda AI, OctoML, Prophecy, Kixo, Rixen Technology, SAP, Silicon Labs, Stream Analyze, and TDKey. So again, thank you everyone for attending today. And again, thanks to Alex and Sam, and hope to see you soon on any of our other tinyML events that we have. Everyone have a wonderful day. See you soon. Bye.
Thank you all. Bye.
Thank you.